It's a pleasure to introduce Regilene Delazari, and she is professor at the Universidade de São Paulo in São Carlos, and her research fields are singularity theory and dynamical systems, with emphasis on singularities of vector fields. Today, Regilene will talk about topological equivalence at infinity of a planar vector field and its principal part defined through the Newton polytope. Thank you, Regilene. And you can begin whenever you're ready. Your microphone is off.
Sorry, could you hear me?
Yes.
Okay.
Yes.
Thank you for the introduction. Sorry for the mistake. It's a really pleasure to be here today. Thank you for the opportunity to discuss a little bit about what I'm studying this period. As Deborah said, my main object of research is the singularities of vector fields. And today I'd like to show you how we can use Newton polytopes or Newton polyhedras to study singularities of vector fields. Such kind of tools, the Newton polytopes, are very, very useful in the study of functions or applications. And now we are trying to generalize these ideas for the vector fields. This is not the first paper about this idea, but we don't have so many results using these tools as for the study of functions. Okay, so let's start. The title of my talk is a little large, but my idea is to show you, to explain what mean each sentence in this title. And I will avoid some technical results, technical parts. I would like to give you a flavor of the result and the reference. If you would like to have more details about, you could see the paper and we could schedule a time to discuss, okay, about this. Of course, that I could answer some questions, no problem, but there are several technical parts that is a little boring to explain here. I would like to start saying that this is a joint work with Thais Dalbello from UFSCar and Otávio Pérez that is a postdoc here at ICMC USP. Okay, so let's fix the notation. From now on, X is the set of all real polynomials vector fields in the plane. And the main objective of this talk is discuss about the existence of an equivalence between a vector field nx and a second vector field that I will denote by y, given by some part of x, looking for the behavior around the infinity. This is not so strange. If you think about functions, for instance, it's usual to try to study like what is the monomials, what is the part of the function that is really important to study some notion, some equivalence between we call the determination, okay, if the function is finite determined or not. So I'm here doing the same. I have a vector field, and I would like to show that just a part of some jets of these vector fields are really important to decide about the solutions. Okay, we could consider like a trunk, not just some jets of the vector fields. But this is not for study the behavior around a point, like a singular point, but around the infinity. I'm looking for the singular points that are at infinity. I will explain the ideas in detail soon. So, of course, that to explain this main objective is necessary to say what it means to be equivalent in this context. Okay, for functions, we have the R equivalence, the A equivalence, and many other kinds of equivalents, and it is usual to use diffeomorphisms between the source, between the target, and sometimes we would like to preserve some properties. But for vector fields, the local equivalence is done by homeomorphism. So we will say that X and R are locally equivalent if there exists a homeomorphism between a neighborhood of the domain, take each solution in this domain for another solution from Y. So the idea is to take a solution to another solution, and sometimes it's necessary to keep the time, sometimes not. So we have what we call the topological equivalence or the conjugacy. Conjugacy means that I would like to keep also the time. I have an interval that I need to, it's necessary to spend t0 minutes to run it. The same happens from the image of this solution. Okay, I'm looking for equivalence, but this is something so new. The answer is no. For instance, the Hartmann-Grobman theorem, that is a very famous theorem in the dynamical systems. I think that everyone who made a ODE course heard about, say exactly something similar that I'm looking for here. Okay, the behavior of the vector field in a singular point that is hyperbolic, the behavior around this point is the same as the linear part of the linear part of the vector field, because there is a homomorphism takes solutions from the original vector field to the linearization, we say. Okay, this condition is that the point must be hyperbolic. Okay, hyperbolic means that the real part of the Jacobian matrix is not, the Jacobian matrix has only eigenvalues with real part non-zero. Okay, but this is not the unique result. Brunel and Miari also generalize in some sense the Hartmann-Grobman theory, studying the behavior of the solutions of a vector fields near a singular point that they consider as the origin under some non-degeneracy conditions using Newton polytopes, except by the case where the solutions turn around the singularity that he called the center focus case. So the idea now in our paper is exactly to generalize these results from Brunel and Miari to study the infinity. Okay, so is what is in this slide. We would like to present some non-degeneracy conditions under which the vector field X in the plane is topologically equivalent to its upper principal part. I will define soon what means upper principal part, defined by the Newton polytope in a neighborhood of the infinity. Okay, I must explain several things here. No, what it means to be non-degenerate, what means a vector field to be non-degenerate, what means a neighborhood of the infinity, what is a upper principal part. So these are the words that I do like to explain for you. So, in other words, the singularity of the original vector field and the vector field defined by the Newton polytope, the singularities at infinity will have the same local behavior. As I mentioned, this is like a generalized version of the Brunel-Miari paper from 1990, and also from Berezovskaya, who worked with similar ideas in 1978. This second paper is not so famous, so known, because it was written in Russia. But okay, why to use Newton polytopes to study polynomial vector fields? This is a natural question. And as I mentioned, these two works have the same approach. They also look for the principal part to study the behavior around a singular point. Alonso Gonzalez in 2015 generalized the ideas of Brunella-Miari for the three-dimensional case. Zupanovic extended this result for the case where the principal part is not so degenerate, is a little degenerate, so she called the generalized principal part. In a paper for 2006, we used the Newton polytope to study the singularities of a positive quadratic differential form, so it's not a vector field, but it's a pair of vector fields. Perez and Silva studied using Newton polytopes to study constraints differential systems. Also, Bruno used this kind of tools to study integral curves of vector fields in the finite and infinite singular points, but in a different context. Okay. Well, we have many other references where the Newton polytopes are used to study some characterization or some dynamic of vector fields, especially in the plane. But although the use of Newton polytopes in the study of planar vector fields is well understood in the literature, as we know, there is no explicit result that guarantees the topological determination of the dynamics of planar polynomial vector fields in a neighborhood of the infinite. So this is what we would like to observe, that is possible. Sorry, I return a little bit. Is possible to apply in this context, okay, to study the behavior of the solutions near of the infinite. Okay, so the question, or the natural question, is why and how to study the infinite? We know how to study a neighborhood of a singular point, but why and how to study what happened so far? Okay, we know, I think you also, that it's natural to think what happens when you are walking along of a solution and where the solutions died, where the solution comes from and is going to. And this could be possible to answer. We could say about this behavior only if we are in a compact space, okay? Because in the compact space, we have all limits of the solution. So the idea to study the infinity is exactly to take the plane and consider a compactification of the plane. So let me show you a picture how the geometric idea to look or to think about the compactification of the plane. I will use my blackboard, in fact, my green board. If the image is not so good for you, please, on the top of my image, you have how to click them and to open a new window where my image is a little bigger than now, okay? Okay, so consider a sphere, okay? And took the plane on the north pole of this sphere. This is my plane, and here I have a vector field. So for instance, we have some solutions, some behavior. I'd like to project, as we made in the singularities, in the study of functions, it's very usual to project the lines or the solutions or the how you say, the trace of the function. I will do the same in the sphere. But how is the best way to do this if I'd like to see the infinite? In the usual, the basic topological course, the more natural thing to do is exactly, if you have the plane, you, like a sheet, you cover the sphere and only to consider a point here. That is what we call the point compactification. No? But this is not good in this situation because we have the infinity as a point. And it's very, very difficult to consider this study here. So the idea of the Poincaré compactification is a little different. What we made is the following. We took a point in the plane and the line passing through this point and the origin of the sphere. Okay, so this line here will intercept the sphere in 2 points. 1 point in the north hemisphere and 1 point in the south. So we say that this point is the projection of this point on the sphere. Okay, so this is what sometimes we denote as something like that. Okay, with a bar. Look that this point is exactly on the sphere, so this means that this distance is 1. And it's possible to give the analytic expression for this vector field. So we could do this for any point in the plane. Of course, that only we cannot say that it's possible to do for the points at infinity. But the points in the infinity of the plane will be in correspondence with the equator. Okay, and we could show this in an analytical way. So we could show that for each point here on the equator, we are looking for a point in the infinity of the plane. So this is what we call, this is the geometric idea of the Poincaré compactification. We have a copy of the plane in the north hemisphere and another copy in the south, and we could extend analytically, in an analytical way, this vector field for the equator. So we have a new vector field here defined in all the sphere. Okay, and this is what we call the Poincaré compactification. If we use the polar coordinates, we could say this, but also we could write this compactification using local charts. So now, returning for my slides, you could see that the equation in 1 and 2 are the analytic expressions of the Poincaré compactification that I try to give you the geometric idea. Okay, this is doing in local charts. So in the equation 1, we have what we call the local chart 1 and V1, and in 2, U2 and V2. It is important to mention that V equal to 0 represents the infinity, and the UV in equation 1 and 2 have different meanings according to the local chart that we are looking for. Okay. This kind of Poincaré compactification appears in several works, but the problem is that when we look for a point at infinity, this point could be very, very degenerate. So it's difficult to discuss about the behavior of the solution around this point because it could be necessary to blow up them. So it's necessary more tools yet. But to solve this problem, we could use another kind of compactification. Sorry, this slide says exactly what I have said before. Okay, UV means have different meanings according to the local chart. It's possible to extend the polynomial vector field to equator, multiplying the vector field, the projected vector field, by a power of V, that here I denote by V delta minus 1, where delta is exactly the degree of the vector field. Remember that I'm looking for vector fields that are polynomials, okay? Only polynomials, vector fields. And so in this order, we could extend the projection to the infinity, to the equator. And this is, okay, V equal to 0 represents the infinity. But as I was saying, the Poincaré-Lyapunov compactification is another kind of compactification. What's the difference between the Poincaré-Lyapunov compactification and the Poincaré compactification? The difference is that after the Poincaré-Lyapunov compactification, if we were able to find good powers, good values of weights, we will have only hyperbolic singular points, not degenerate ones. Okay, so let me give you the geometric idea from this second type or another kind of compactification. To do that, consider a pair of positive integers denoted by alpha and beta, and denoted by cosine theta and sin theta, the unique solution of the Cauchy problem written here in this slide. See that this is not the usual cosine and sin theta trigonometric functions, okay? I call them as a generalized one because we have now powers, alpha and beta, okay? So according to alpha and beta, as they are analytic functions and periodic ones, we have a unique solution, and more, they are analytic. The solutions are analytic with period given by 3. Okay, but why I'm looking for? I'm saying about that. What is the relation this with? I try to draw here. This is a kind of expression who give us a generalization of polar coordinates. Okay, we have now here a generalization of polar coordinates. It's like a polar coordinates with weights and also with generalized functions. They are not usual cosine and sin. They are generalized ones. But works exactly with the same geometric idea, okay? Applying them, we have a compactification of X in a disk or in a sphere, if you prefer to say, which depends on alpha and beta. And this is what we denote by the d alpha beta, because we are looking for Poincare-Lyapunov compactification with weights alpha and beta. Of course, that is very difficult to work with this cosine and sin. So we choose to look for this expression using directional charts or local charts. Exactly as we work in the plane, as in the sphere, we could consider local charts. The charts where x is positive, x is negative, y is positive, y is negative, z is positive, z is negative. So in fact, we have 6 local charts, but only in the charts which we could see the equator, we have points from the infinity, okay? So where z is positive or z is negative, we don't have points at infinity, so we are not interested on them in this moment. In 5 and 6, we have exactly the expression of the local change of coordinates of this Poincare-Lyapunov compactification. If you compare with the previous expression that I have denoted by 1 and 2 before, we have exactly the same expressions if alpha equal to beta equal to 1. Okay, so it's exactly a generalization. So we could say that is a compactification with weights. Again, U and V have different meanings in each local chart. V equal to 0 corresponds to infinity, and as I have mentioned, if alpha equal to beta equal to 1, we are exactly in the Poincare compactification. So it's just a generalization. Okay. So now, how to use this? What is the impact? What is what happens if we apply this kind of compactification in a vector field? And how is the better way to do it? So let's take a vector field X and written as the sum of the quasi-homogeneous polynomials vector fields. This means to write X as in 7, okay? Instead to work as the constant, but plus degree 1, plus degree 2, as usually we write, we are looking for a decomposition of the vector field according to quasi-homogeneous parts. The D, which appears here, so if you look just for the part which satisfies alpha m plus beta n equal to d, this is what we call the d level of the alpha-beta decomposition. Look that in 7, we have x written as the sum of the d levels of alpha-beta decomposition. Okay, so this is always possible to do. It's not a restriction. Any vector field, polynomial vector field, could be written as the sum of quasi-homogeneous vector fields. Well, the natural question is how to find alpha and beta. Look that we need to know alpha and beta to write in this way. And what is the advantage to use this kind of compactification in this vector field? Okay, if we apply the Poincaré compactification, for instance, in the U1 chart in X, we have the expression in 8. It's interesting to see that here we have something that is linear, okay? It's like a linear vector field multiplied by a power of U and V. If we were able to choose good values of alpha and beta, maybe we could do this as 0 or 1. So this is the main point, okay? And the same happens for the second chart. Also, we have expression which depends only of this power. So look that I'm trying to see what is really important. What is the part which will give me the information which is important to study of the solutions. Okay, I am looking for jets. So it's a different kind of a way to see jets of this vector field. Okay, but here I'm just saying, remember that as we have weights, now it's necessary to see the positive and the negative direction. I return a little bit, excuse me. Here we have powers which will depend. D is the sum, so this could be positive or negative and could change signs, could change solutions and directions. So we must to see for the positive direction and also for the negative direction. But the expressions will be very similar. Of course, that when we are analyzing the vector field, we must to consider both. Again, v equal to 0 represents the infinite. But now the question, how to obtain the good values of alpha and beta? This is the third part of my talk, because I told you what it means to be equivalent, what means to how I could see the infinite in the plane, and now where is the Newton polytopes? Exactly this point. To find the good values of alpha and beta, we will use Newton polytopes. Let's show you how to do that. In 10, we have the expression of the vector field written as sum of quasi-homogeneous part. Okay, considering this vector field, we will define what is known as the support of the vector field. What means the support? I will consider the powers xm and ym and took this pair of positive integers as part of the support of the vector field, since this a mn or b of mn is non-zero. So this is what is written here, okay? Each pair mn where this or this parameter is non-zero is a pair that will be in the support of X. Observe that as we are in the case where X is a polynomial, the support will have finite points, okay, a finite number of points. And so we could define the Newton polytope associated to the vector field X as the convex hull of the support. So this means that if we have P0, P1, P2, P3, P4, and other points here, we just took the biggest polytope, which the faces are exact with vertices in these points, okay? So in this case, we have this part that will be the lower part of the Newton polytope in blue, and in green, we have the upper part of the Newton polytope. Of course, that we could have points of the support inside of the Newton polytope, okay? They will be here, no problem. So remember that the PIs, which appears here, are points on the support, and the faces of the Newton polytope is the segment joined to vertices, okay? The interior of P will be empty only when P is a segment, okay? Of course, that this could be happens. For instance, if you have only points in one face or two faces, no problem. But we are interested in the case where the Newton polytope is non-empty. So I just moved the previous figure for this slide. It's important to observe that we have vertices, we have the boundary of the Newton polytopes as the union of a finite number of compact segments, and the convex envelope of this S will give me what we denote as P plus, okay? This is the part, the positive part here, and the boundary of, the P plus is the envelope, the convex envelope. I'm saying what? If I took here the sum, okay, the convex envelope for each point, okay, we were able to define the blue part of the Newton polytope. In fact, the blue part is what we call the boundary, and we denote it in this way, the boundary or the lower boundary of the Newton polytope. But why I'm saying these details here? Because I needed to define what means the upper boundary of P. This is what will be really important in our result, okay? So let P be the Newton polytope with a non-empty interior. We define the lower boundary of P as the union of the compact segments that are in the boundary of the convex envelope, and from now on, we denote it by PL, and the upper boundary of P is the closure of the boundary of P minus the lower boundary of P, okay? This, to have a geometric figure, I return a little bit. The upper principal part will be this part in blue, okay? Will be the top, what is not in the positive part, but is close, is the boundary of the Newton polytope, but is not in the lower part. Okay, let's see now how to use these ideas. I will give you an example. X is a vector field. I took the support of this vector field here, okay? Let me show you. -1, 3 is in the support because as I have here y3, and it is necessary to have an x here, the monomials here will be equals to -1 y3, okay? So here the basis is x ddx and y ddy. So to have x here, it is necessary to have -1, 3. For this monomial, I have an x here, so here the number is 2, okay? And y with power 1, and so on, okay? So there is a specific basis that is necessary to choose to define the support of a vector field. If this is the support, now we have this Newton polytope here, okay? In blue is the lower part, in green, the upper principal part. So what I would like to show you is that only the monomials on the upper principal part are relevant to study the singularities at infinity, as Brunello and Miari show that only the monomials on the lower principal part are relevant to study the behavior of the singularity at origin. Okay, it's a complement. Okay, but how to do that? And what is the mechanism, or what is the theory with the guarantee that this happens? So, given a Newton polytope with non-empty interior and gamma, a face of the boundary of P, we know that this face satisfies this condition. So we have each monomial of the vector field that is in the boundary of the monomials, the Newton polytope, or each Mn, each pair Mn satisfies this condition because it is in a line, okay? And this vector field, mu and v, which satisfies the condition, is exactly a normal vector field to the face. So, for instance, if this is the point Mn, this vector field here is a vector field which satisfies this condition for some d. And if the vector field is inward, so we have a sign. If it's in an opposite sense, we have another sign of d. So if d is positive, we say we have, let me explain again, sorry. I would like to define a special collection of vector fields. Of course, that there are two normals vector field to each face. The one in this sense and the other in this direction, the other direction. But I would like to define a special class, the class which will be important to define the diffeomorphism that I need, okay? So I will choose this collection in the following way. Consider all the faces in the Newton polytope, okay? In the boundary of the Newton polytope. And for each face, choose the normal vector field, which is inward, what means that is going inside of the Newton polytope, okay? Denote by this collection of vector field in this way, okay? Using this collection, we will define the main part of this change of the coordinates. We define what is known as a skeleton. A skeleton is exactly the collection of the inward vector fields associated to the Newton polytope, where two vector, the coordinates of the vector fields are primes, so are coprimes, okay? And we will add more vector fields to this collection with these following properties. So let me repeat. I choose these inward vector fields. This is what is here. And now I will add vector field in this collection in the following form. The first vector field from this, the biggest, this increased collection will be 0, 1, and the last one will be 1, 0. If I add vector fields in this collection, it's necessary that each vector field has coprime coordinates, and the determinant between two vector fields is always 1. This is not a restriction. We always could do that, okay? Moreover, two consecutive vector fields cannot be normal to consecutive segments of the Newton polytope. This means that if I had two consecutive vector fields in the original collection, I must to add a third vector field between them, satisfying 3, to have 4 satisfied also, okay? And finally, this collection that I define must be minimal, in the sense that there is no other collection satisfying the previous conditions with a smaller number of vectors, okay? So, looks like so big, but it's not, okay? We always could build this kind of skeleton, okay? And using this skeleton, we could define what will be the local charts, okay? Exactly as in differential geometry, we have local charts to study the sphere. Now we have a local charts to define, to study a manifold. And what is the theory which guarantees that? Is exactly the toric geometry, okay? The toric or the toric geometry is with guarantees that this collection is good, there exists, could be done, and using them, we could okay. I must before to go on, I must observe that the condition that two vector fields have determinant equal to 1, this condition here, guarantees that each pair, consecutive pairs of a vector field in the skeleton is a basis of Z2. Okay, remember that we are looking for vector fields with positive coordinates. Okay. Okay, so now we are able to define our manifold and our collection of local charts. Okay. In fact, using each pair of vector field, we could define this change of coordinates. Look that they are diffeomorphism outside of the axis, okay? And also for the case where we have the first and the last vector field, we also have these expressions here that are exactly the expressions that I have showed you before when I mentioned the Poincaré-Lyapunov compactification. So again, I'm generalizing the Poincaré compactification, okay? I'm doing like the Poincaré compactification in steps, okay? I will do that in each phase, in fact, okay? This is the process here. And so we could say that we have a compactification of the plane except by the axis, okay? This star means that this compactification is not well defined when u and v equal to 0, but this is what we call the compactification of the plane adapted to the Newton polytope. So we have a manifold, a smooth and compact two-dimension manifold, contained in the plane except by the axis, and the local charts defined in pairs of this skeleton that I have mentioned before, and this collection will cover all the manifolds. Okay, so it's exactly the idea, the geometric ideas that we have in the differential geometry in the sphere now is generalized for these cases with weights and adapted to the Newton polytope. Okay, so using toric varieties, we get this manifold. Of course, that this manifold is doing over C, and is smooth over C, but also over R is smooth and compact. Okay, these are the details that I have mentioned to you in the beginning that I will not give you details. Okay, it's so technical conditions. I prefer just to explain the ideas, the geometric ideas, and not the technical part. Okay. Okay, so I could say that we have a compactification of the vector field X adapted to the Newton polytope, exactly when you consider, as in this geometric idea here, the projection of the vector field from M to the tangent space of M using the pullback of X, exactly from the local, applying the local charts, okay? And these local charts are, in fact, diffeomorphism outside of the coordinate x. Xj can be analytically extended to the set, what means that we could extend it analytically to the infinite again. This extension we denote by xj bar. The domain of xj bar is the set uj, and u equal to v equal to uv equal to 0 plays the whole of the infinity. So now it's not only v equal to 0, okay? It's exactly where the vector field the original vector field after projection is not defined. We extended it, so we have the infinite. In my mind, what I have is that my picture like this, okay? I'm doing, maybe this way, I'm doing a work in pieces, okay? I don't have more a circle, but I have something that is topologically equivalent to S1 as the infinite, okay? These parts, these are the axes. Okay, so let me give you an example to try to explain a little bit better. This is exactly the previous example, okay? I have given you before the Newton polytope, and now I would like to explain how to obtain the skeleton using the previous idea. So here, these are the inward vector fields, okay, that I have before. I have shown before. I don't. Sorry, the picture is not here anymore. But if these are in the, did you remember that we have three faces in the upper principal part? Okay, so these are exactly the vector fields, the inward normal vector field to these three green upper faces. Okay, and to build the skeleton, we need to include this first and this last vector. Between this and this, I must add this vector. If you consider the determinant between these two is equal to 1, between these two is equal to 1, between this and this, they are here, it's necessary to add this vector field, but in an order that the determinant between this and this is 1, and so on. So this is the way that we build this collection. And using this collection, we could apply the process, okay? We could find the alpha and beta in each local part, in each phase. So to state the main result, I mean almost in the end, we need to introduce what we will call the upper principal part of X. The upper principal part is exactly the restriction of the original vector field to the monomials which are in the face, in the upper principal part of the Newton polytope. So in the previous example, we have three faces. So I will consider only the monomials that are in that face. The monomials that are not in the upper principal part are not part of this vector field, okay? They do not appear in the expression. So it's a way to consider a jet, but not the minimal ones, but the biggest ones, okay? I start from the top to back. Okay, and we will say that our upper principal part is non-degenerate if when we restrict the vector field to each face of the upper principal part, this vector field restricted to the face of the upper principal part has no singularities outside of the axis. So is not allowed to have a singularity outside from the axis. If this happens, the upper principal part is degenerate. If you don't have singularity outside of the axis, we have, for any face of the upper principal part, we have that the upper principal part is non-degenerate. Okay? This is the concept. This is the non-degeneracy condition. Okay. What is important to mention is that the set of all polynomials vector fields with non-degenerate upper principal part is an open and dense set in the set of all polynomials in the plane. So in fact, this is a non-degeneracy condition, okay? As in the hyperbolic singular points, we have the same thing here. Finally, we must introduce one more condition to guarantee our result. So a planar vector field Y is said free of characteristic orbits near of the infinite if its compactification has no singularities on the boundary of the Poincaré-Lyapunov disk. What this means? This means that if you look for this region, we cannot have the situation where the solution turns around, okay? We cannot control the situation. So this case corresponds to the case where the vector field is free of a characteristic orbit. So what it means not to be free of characteristic orbit? Means that we will have some singular point here, and we will have a separatrix, okay? It's necessary to have a separatrix. If I have a singular point without separatrix, this is not good for our construction, okay? It's necessary to have a singular point with a separatrix, so with a characteristic orbit at infinity. And finally, we must say what it means to vector fields to be topologically equivalent at infinity, because I told you before what it means to be equivalent near a point. Okay, we took a neighborhood, and for each solution here, we have a new solution in the other vector field. But what happens at infinity? So the idea is to see what happens in a neighborhood of infinity. So I took like a neighborhood of the infinite, and I will apply the equivalence that I have mentioned before for this case. If I have a solution here, this solution will be taken to another solution, or to a solution from the other vector field, and there is a homeomorphism from this neighborhood from the other neighborhood. So the idea is to extend the concept of topological equivalence, where I'm not worried about the time. So this is, in fact, a topological equivalence is not a conjugacy. So what is written here in the definition is that there is a neighborhood W1 and another neighborhood of W2 from X and from Y. There is a homeomorphism which takes this neighborhood to the other, and this same homeomorphism took each solution here to a solution in another neighborhood. Okay, it's the local equivalence at infinity. So it's like you have a ring. Okay, a ring where the equivalence is local. Okay, so now I'm able to state our main result to finish. Okay, a vector field in the plane, a polynomial vector field with non-degenerate upper principal part. So remember, non-degenerate upper principal part means that if you restrict the vector field to each face on the upper principal part, the singularities are only on the axis. And suppose that the same vector field is not free of characteristic orbits near the infinity. So if I have a singular point, it's necessary to have a separatrix or a characteristic orbit. Under these conditions, we also suppose that the vector field, the upper principal part of the vector field, does not have curve of singularities. In other words, the singularities, the singularities of these vector fields are isolated. Okay, we cannot control if we have non-isolated singularities. Under this condition, the original vector field is topologically equivalent to the vector field obtained by the restriction of the original vector field to the monomials that are in the upper principal part of the Newton polytope near of the infinity. So we could present a condition, a non-degeneration condition, to have an equivalence from the original vector field and the vector field obtaining restriction the vector field only for the monomials in the upper principal part. And then why? What is the main ingredient in this case? Okay. Well, the main ingredient, sorry, I will change this. I will not say much about this because of the time, but the main ingredient is this. In fact, is the effect of the non-degeneracy conditions in the infinite singularities. when we choose that kind of compactification, the alpha-beta compactification or the compactification associated to the Newton polytope, when we apply this kind of change of coordinates, the singularities at infinity will be hyperbolic or semi-hyperbolic. So will not be degenerated. So we could say what is the behavior around or near of each singularity at infinity. And as we have separatrix, we could use the glue lemma to glue the solutions and obtain the behavior around the infinity by gluing the solutions at infinity. So this is why we have so many restrictions, okay? It's necessary to have a characteristic orbit to glue. It's necessary to find good alpha and beta to have the desingularization of the singular points at infinity. And we cannot accept the condition to have singularities outside of the axis, because in this case, we will not desingularize the singular points at infinity. This is the main ingredient that is inside of the proof of this result. Okay, so I said I spent many time in this case. I think it's enough to say no, to give an idea about this work. I will just finish presenting you the main references. The first reference here is the paper which motivated our study, and they are very famous and which appear in many references. This is our paper now, where we present details about my talk today. And this is a book where if you are interested in to say or to know a little bit more about the qualitative theory of planar polynomial vector fields, is a good reference. Okay, thank you so much for your attention, and I'm open to